All right. So some of you already have heard this talk a few months ago. So for those, just bear with me for this 10 minutes. So this is a work done with a very bright master student, former master student, Yogesh Reddy, and also with Satya. So considering the late hours, I'm going to talk about really something very simple. The idea is to use very simple illustrative examples at the end to arrive at some rather simple understanding about some problem that I'm thinking about. So for that, let me explain what is this dynamical phase transition that you already also heard in the talk of Muktesh. So for me, the dynamical phase transition in this context is our sudden change in the statistics of dynamical observable is the dynamical phase transitions. So let me give you an example, and this is a very specific case. So this is a cooked up example of one Brownian particle in a periodic potential on a ring. If the force is zero, it's just in a potential, then we know at a large time limit it will be equilibrium state, and the position distribution will be e to the power minus beta u, which is the Maxwell-Boltzmann distribution. Now, if there is a force, driving force, which is driving it in the constantly, then the stationary state is non-equilibrium, and the probability distribution has an exact formula actually given in this book of Riskin, and it's a sum of two exponentials. Now in this, if you ask that if I look at the low temperature limit and I still try to write it the probability distribution in a Boltzmann-Gibbs form, then it would come in this kind of, you can still write it in this kind of form, and this phi function, which is known as the large deviation function, and this function looks something like in this green color, and it has certain singularity, okay? And these singularities are often considered as the dynamical phase transition. For this, where the dynamics come from is rather easy to understand, that if you are looking for the probabilities for any positions here, all the paths that really contribute is the path that directly crawls up to this height. If you're trying to come to this site, then you have two options. One is to crawl in this longer height and come here. The other one would be to go on the other direction and come up to this point and go down the hill, which doesn't cost much. So for all these parts of the position, the cost function is equal to the height of this point. So there is a switching of these paths the way you create the fluctuation across this point. So that's the dynamical phase transition. Now the kind of things that I'm going to talk about here are about fluctuation in empirical observables, which are time integrated observables. For example, you take the same problem and now look at the observable, which is the time integration of these velocities. And if you write down the corresponding probability at the large time limit and in the weak noise or the low temperature limit, it also has this kind of phi function, the large division function, and it has a kink. And this is known as the dynamical phase transitions. Now, this kind of feature has observed in many, many contexts, some experiments done by Ajay and others, some other examples of lattice models, many works of Satya has seen this kind of singularities. Okay? Now, a question that was asked quite some time ago, and people wondered that, can these kind of dynamical phase transition appear in systems which are not macroscopic, but that of a single degree freedom problems, also which is equivalent of not weak noise limit, okay? But there are already examples that you can actually see such kind of singularity. So for example, if you take a drifted Brownian motion in 1D line, infinite line, develop certain singularities, okay? Now there were also many, many other examples of these single degree freedom problems without taking any weak noise limit where this kind of singularities emerge. The question that we wondered is that, is there, at least in some of these class of models, is there some commonality between all these? So this I will try to explain to you using very simple illustrative examples. So what's the picture that emerges? Let's take this very simple example, this cooked up example. Take one Brownian particle with certain death rate alpha. Okay, so the particle evolves and with certain rate it dies, and when it dies it doesn't move anymore. Let's ask in this question, what's the probability of the position of the particle at certain time t? You can solve this problem and find that it has this similar exponential distribution, and this phi function also again has this kind of kink, which looks which is identical to the same resetting problem that I showed you. For the same problem, you can also ask what's the distribution of the area under the curve. For large time, it also has a similar asymptotic with different scaling. It also has this large deviation with this some kind of singularity. You can look for the residence time. It also has a very similar feature. Okay, so you can now look at another problem. Take a Brownian motion in presence of an absorbing wall. So the particle could go and get stuck there and dies there. You ask similar question, what's the residence time distribution? The residence time distribution also has this kind of singularity. If you look at the large deviations, you can ask for the area, it also has the similarity. So now, given these two illustrative examples, what's the common thing between the two? The common thing is that there is a competition between survival and diffusion. Okay? So in general, you would expect whenever there is such kind of competition, or in more commonly, if there is some leaking probability, then you would expect this kind of dynamical phase transition. And it is indeed the case. So you can cook up even simpler examples. So think about just three-state Markov chain. So this is a three-state. One of them is an absorbing side. So when you move to that side, you can't get out of it. And you ask this question about what's the residence time distribution. You can solve this problem. You will find that there is such a kink and there is a dynamical phase transition. Take four-side problem. And again, let's say there is this side, which is the absorbing side. And you can ask, what's, let's say, the current distribution, okay? It also has a very similar kink, and it has the similar dynamical phase transitions. So it turns out that in general, whenever you have your phase space has this kind of transient recurrent structure, that you are in a state from which you get out and go into another state, and you cannot come out from there, then in general, for this kind of time-integrated quantities, you will have dynamical phase transition. And once you understand this, you can cook up all sorts of exotic examples. So for example, if you take the same decaying Brownian motion, and now you take many, many decaying Brownian motion whose death rate depends on how many alive particles are there. It's like your death rate depends on how many infectious people are around. And you ask the same question, let's say, what's the net total displacement of the position of all the particles? When you make a plot of those, the corresponding probability has the similar asymptotics, and the corresponding large deviation function has now multiple such singularities with different kinds of orders of phase transitions. And here it really happens because the phase space has this kind of many, many transient states and one recurrent kind of structure. Okay? Now, if you understand this, then you will very soon also get convinced that it would also work for even for non-Markov processes. Take those examples that I showed you to make them active or even fractional Brownian motion. Many of these has similar kind of dynamical phase transitions. Okay? So out of all this, the message that I wanted to pass it to you, that if your phase space distribution has this, if your phase space has, or the state space has this kind of transient and recurrent structure, then if you look for any time-integrated observables, then those distribution develop singularities, which are those dynamical phase transitions. And those phase transition really happens between the competition between to survive in this stage and movement around these transient state space. And this would happen irrespective of whether your state space is finite, continuous, or large or not. Okay? Now, what I did not tell you how we derive these problems, solve these problems. So this could be analyzed using the framework that Satya had developed. Also, there is another way you can study these problems is something called a tilted operator formalism. In these, one feature that comes out that these existence of phase transitions has some relation to the way you see phase transitions in Ising models, where the phase transition occurs because the largest eigenvalue of the transfer matrix crosses. And exactly the same structure goes around here. And you would find that these kind of structures, whenever it emerges, the corresponding Markov generator has a reducible structure, which allows you to have the degenerate largest eigenvalue. So in that way, having the dynamical phase transition has a direct connection with that of phase transitions, or at least at the algebraic level, has connection to the phase transition in equilibrium systems. With that, I thank you for your attention.
If there are no questions, let us thank the speaker.